We've talked about norms on finite sets. Now I'd like to talk about norms on signals. Signals, of course, are much more dense than a finite set and have a lot more values, so we can't use exactly the same definitions for our common norms. So remember that a norm generally tells us about the size of something, the magnitude of something, and you've probably already used it as an absolute value. A norm has to have four properties for some signal. So first of all, the norm of the signal must always be greater than or equal to 0. And it has to be equal to 0 if and only if the signal is 0 for all time t. So again, we're talking about a signal. A signal has to be defined for all values of time. Or in some cases, it may be defined as 0 until time t equals to 0. The third step is the ability to say that if alpha, some scalar value alpha, is multiplied by the signal, then we can take alpha outside the norm and multiply its absolute value. So this is true for all alphas inside the real numbers. And then we have the old triangular inequality. So this tells us that the sum of two signals, the norm of the sum, is less than or equal to the norms of the individual signals summed together. So here, again, we're not talking about a specific function. We're saying that if you want to define a norm as a function, you can annotate it with these parallel lines on either side, only if these conditions are met. So if you want to define a norm, it has to obey these constraints. Otherwise, you can call it something else. So let's define a few norms. Well, the one norm is defined as the integral from minus infinity to infinity of the absolute value of the signal dt. So integral minus infinity infinity, absolute value of u of t dt gives us the one norm. This is the integral of the absolute value. And again, it's a lot like the taxicab algorithm. So this is going to sum up all the values. You don't get anything for free. It's going to be a pretty big number if you have a signal that's non-zero for a long time. So one question, does this exhibit all four properties of a norm? Remember that these are the four properties. So I won't talk about it here, but you may want to consider this as an exercise. Can you satisfy yourself that you could show this for this very simple norm, that these properties are exhibited by this norm? You may want to try doing this just to know that you can do it for yourself. So what's the 2 norm? Well, previously we defined it using the summing operator. Now we're going to define it using the integrand. So here we're going to integrate u of t squared dt and then take the square root after we've finished with the integration. So we can use the 2 norm for relating instantaneous power and instantaneous energy. So these are interesting properties of a particular signal. How much power is in the signal, or how much energy is in the signal? Well, it's not really in the signal, but when we think of the signal in terms of its basic component parts, sometimes we can, for example, think about its RMS value. So let's say we have an ideal circuit, and it's a unit circuit with 1 ohm, with current u of t passing through it. So then we could describe the power as I squared R, so this is the well-known definition for power. If R is equal to 1, then the power is just equal to u of t squared. So this is the idealized power of a signal with a unit resistor through which the signal is passing. The energy is the integral of power with respect to time. So integral of p dt for all time. So remember that the 2 norm is defined as the square root of the integral of power, because power is u squared of t squared, u of t squared. So the integral of power dt squared gives us the square of the 2 norm. So the energy, if we take the 2 norm and square it, that gives us the energy of the signal. So before we talk about the infinity norm, we have to define something called the supremum. So the supremum is the smallest value that's larger than or equal to all other values in a particular set, or in this case a superdense set. So in this case, we have u of t equal to sine of t. What's the supremum of u of t? Well, it's equal to 1 because that's the largest value sine is ever going to have. So why can't we just say that the supremum is the same as the max value? After all, the maximum value of sine of t is equal to 1. Well, here's an example where we have some function 3 minus e to the minus 10t. So this e to the minus 10t is going to get pretty small, and it's going to get pretty small pretty fast. The supremum of u of t is equal to 3 because that's the smallest value that's larger than all the other values, or equal to all the other values that u of t will ever have. But u of t is never actually equal to 3. So u of t is smaller than 3 for all t. No matter what value you choose for t and how big it is, it's going to be non-zero for e to the minus 10 times that t. And so you're going to get a number that's not quite 3, but it's exponentially, infinitesimally going to approach 3. So it's analogous to the least upper bound here, but it's not the maximum value, because u of t never actually equals 3. So we have this magical thing called the supremum that allows us to basically say the same thing that Max says, but in a mathematically convenient way. So the infinity norm then is the supremum of all the individual signal values, their absolute value of u of t. So now that we take this signal, we take its absolute value, and then we try to find the smallest value that's greater than or equal to the values that we see here. So this is the least upper bound of the absolute value. So for 1 minus e to the minus t, the infinity norm is equal to 1. Similarly, here we have the infinity norm equal to 6, because cosine of t is equal to 0 for some of the values. The cosine of t when t equals to 0 is equal to 1, and we're going to have 5 plus 1 times 1. The infinity norm here for 3 to the e minus 2t plus e to the t is equal to infinity. That is, there's no real least upper bound. So the infinity norm is equal to infinity here.